Thanks so much. Thanks for inviting me. Thanks for having me. It's nice to be here. There are some familiar faces here, folks that I recognize. So thanks for taking the time to listen to me. Okay, so I decided to append a colon to my talk title because I'm really going to be talking about wave behavior, COVID-19 wave behavior today. And this is all joint work with Nick James, who is he's actually here today on the call, but I think he's driving or something. So thanks, Nick, for joining. Okay, so here's the structure of my presentation. I'll talk about motivating questions. I think then most of the time of the talk will be dedicated to mathematical approaches to pandemic waves, right? And some methodology that I'll lay out, and some kind of questions about different ways to do this. I mean, I think there are all sorts of future pathways, and where we could modify these approaches a little bit. I'll talk briefly about results, and then I'll end with some ramblings. Okay, which would be fun. All right. So these are my broad motivating questions. COVID-19 has been extremely difficult to predict, and personally, I guess this is the wrong crowd to. This is it's wrong to say this to an AI4Pandemics trial, but I often question whether prediction basically works at all, right? I think that if human behavior is so complicated, and the behavior of COVID-19 cases trajectories have just been so confusing in so many different ways that I kind of ask myself, does prediction work at all? In particular, do the litany of models out there, starting from SIR and then SEIR squared, R squared, V squared, Q to the 4, do they all work? I've just seen like growing lists. I've reviewed papers with like growing lists of these models. And with prediction very difficult, I think that maybe we should describe rather than predict, what's going on, at least for now. And maybe we need a transformational kind of approach later. Not that I'll provide that, but hopefully others will provide that to study future pandemics. So I begin today with the question of what are the most important features of the pandemic to study, and my answer to that, my motivation is COVID-19 waves, right? For various reasons. So I've read so many popular articles, so many newspaper articles that are along the lines of we're just so shocked about either an increase or also a decrease, right? A precipitous increase or decrease in cases in some location, wherever that may be. And that's just been a consistent feature, that this has been very surprising, difficult to understand and predict. And everyone has consistently been caught off guard by the next wave of COVID, time and time again. I think the decreases are probably the most interesting there. And so COVID-19 waves, they may fascinate or terrify the public. They may prompt politicians to urgent action in the increase, or premature relaxation in the decrease. And as I said, they may perplex scientists. Here specifically were some questions that motivated the papers and the work that I'm going to talk about today. Back in June 2020, the US was in a massive, for the time, of course, our current cases have blown that idea of massive out of proportion, but at the time, the US was in a massive second wave. Let's investigate it closer. Let's determine which states are in a second wave, and that results in some kind of classification problem. And I thought, and that's going to be mathematically interesting to try and develop a framework to classify. And the other question that I think I won't have much time, but I'll touch on it briefly, is the other motivating question is that in the second wave of COVID-19 in Europe, which happened later in 2020, I noticed just from my friends, basically, in the data they sent me, that the second wave had a much lower fatality rate than the first. And how does this differ over the countries? What's the full story there? And it turns out that the media was not really kind of giving a full story of what was happening in Europe and the heterogeneity within Europe. Okay, so now I'm going to talk about some mathematical approaches. And again, this is all to study wave behavior. Okay, so let xt be a time series, new daily cases for a given locality, a country, a state. And I think understanding the wave behavior, namely dividing the epidemic for that country or locality into first and second waves, really depends on defining non-trivial turning points, local maxima and minima, and then using that to divide the function into discrete waves. Okay. So, and then the next question is, okay, so not just for one state, but what if you have multiple states? How can you distinguish them, distinguish their wave behavior? Okay. First step, relatively easy. You can, smooth up the cases. Next step, also relatively naive. You could use some smooth function interpolating through, differentiate, or some kind of naive definition as written here. Let's just pick an interval length and select a local max by the property that it is. Did I say interval? I'm an interval that it's the local max in a given interval. That's a first naive definition. Okay, that's where to start. And the first thing that I found quite interesting is that this definition is actually not very good. It has some subtle flaws where you can actually detect, two adjacent peaks. For example, two adjacent troughs, which doesn't, or like local minima, which doesn't really make sense, and it would also detect, too many peaks if there are equal values, and also using differentiation that may be unnecessarily complex and may depend substantially on the precise method of smoothing. Okay, so let's move to a slightly less naive option. Instead of using a definition such as this, we can essentially use a recursive or inductive procedure to continually update a growing list of peaks and troughs. So basically, if we have a peak, we will use some relatively simple conditions to determine what is either the next trough or the next peak. And if a greater value is observed, we can discard this and update it with this. And otherwise, we can add the next trough to this. Okay. Sorry, there is a lot of distraction going on right now. I don't know if you can hear there's crying and tradies and all sorts of things. Okay. Okay. All right. Okay, so what I outline here gives one procedure to continually form a list of peaks and troughs for a given time series. Okay, but then we get to the more interesting question of refinement. Okay, so refinement is basically what we need in order to only leave behind non-trivial peaks and troughs. Okay, and this is the whole point, right? We want to determine, an excessively coarse definition of a peak and trough would, lead to too many undulations detected when in the absence of a significant decrease of cases that can be determined at the end of a first wave. All right, and so this is when things get mathematically interesting. So here we have Georgia and Florida, data up to, I think, the end of July. Okay, and of course, these case counts have been, completely exceeded, since then. But Nick and I spent a great deal of time looking at data such as this, looking at time series such as this. And essentially, if we looked very hard at Georgia, both kind of qualitatively and then using several different methods to include or exclude these turning points. But we looked very hard at Georgia, and this is probably the most difficult case in terms of, this is the most difficult pictorial example of our methodology, choosing one decision for one state and the other decision for the other state. But even to this day, I look at Georgia, and I look at, there's a peak here, but it's probably just a single day of reporting, and it's cancelled out by this. even though the smoothed cases do exhibit a small peak, a small local max here and a small local min there, I'm not really confident that this was ever any sort of decline at all. Okay, so here and here, they basically level out. Everything seems to level out. It seems to be actually very, very flat. So I would not call this a period of non-trivial increase to a max and then decrease to a local min. But here there is actually, and again, this is like the boundary case. This is the most interesting case where parameters just work out to declare one thing a noticeable decrease and the other thing not. Here in Florida, I do see more of a decrease. And again, these examples don't demonstrate. I don't think these. I don't present these examples to claim a victory. In the methodology, I use these examples to claim that there are subtle decisions and cutoffs to be made with these various parameters that might determine one state to have exhibited a second wave and the other state not to really have exhibited a completed first wave. Okay. Anyway, so what's the difference? What's the difference between Georgia and Florida? That was codified in our refinement conditions. Okay, so in this paper 1, which studies COVID in the United States up until its second wave in June, July 2020, we ended up using 2 conditions to eliminate immaterial peaks and troughs. One was, we termed it a peak ratio, where subsequent peaks were considered immaterial if they were extremely small relative to the first peak. That played out in states like New York, where there was a very great first peak, essentially no second peak, and so we decided to term that one first wave conquered without a second wave beginning. That was the function of the peak ratio, and then we imposed some degree. We declared that some degree of decrease was necessary between a permitted peak and trough, and we defined this quantity, the log gradient, to do so. Now, the log gradient is essentially a logarithmic rate of increase, right? It's a more appropriate substitution for the raw rate of increase, for example, and I think it's inspired by the fact that in finance you measure log returns rather than raw returns in order to get a quantity that is symmetrically bounded between minus infinity to infinity rather than -1 to infinity. And it's funny, we kind of fiddled around with various different parameters, various different rules, and in the end, I think that the epsilon equals 0.01 parameter, a 1% logarithmic or logarithmic increase or decrease rate, was a suitable parameter that really worked well with our data and appropriately determined, at least in our eyes, some states to be first wave states and some states to be second wave states. So I think it's interesting that it ended up being this clean. And so, for example, with this log grad refinement rule, we were able to this peak to trough was considered immaterial from Georgia and eliminated. So Georgia was determined to be in its first wave, and Florida was determined to have a small first wave and then a second wave. Now, of course, there are countless alternatives to refinement. Okay, and retaining non-trivial peaks and troughs. And so, for instance, in subsequent work, we change this up a little bit. When we had longer time series, we imposed a global peak ratio condition where any peak that was not, a required proportion of the global max of the time series was eliminated. And so, again, all these different conditions are incorporated in the, inductive updating or adding procedure described here. So this procedure where you continually update a list of peaks and troughs, either adding new troughs or kind of updating, removing this peak, replacing it with this peak over here, all these additional conditions are incorporated in that procedure. And so we updated the peak ratio condition and the log gradient condition. That has its flaws too, especially over longer periods of time where you actually do exhibit very slow declines that you want to where you don't want to refine and remove out peaks and troughs. So there are all sorts of different approaches here. We could obviously use a kind of raw gradient rather than a log gradient condition, and many other approaches. So this classification problem of determining non-trivial peaks and troughs and therefore non-trivial waves of a time series is something that's mathematically interesting, and we've only just proposed a few ideas, and who knows the other approaches. Okay, and so that was the more interesting question. Then I think the most interesting question is the question of distinguishing different behaviors of different states. Okay, so I said above, what instead if you have two localities with case time series xt and yt? Okay, so our approach in several papers was we've used this semi-metric between finite sets in a number of instances. It's essentially a modification of the modified Hausdorff distance. So you can say modified squared Hausdorff distance. And then we can use this semi-metric between sets of peaks, and sets of troughs, to get a symmetric quantity, which is zero if and only if the two countries have the exact same wave behavior. Okay, and this worked very well early on, right? This worked very well with data that was in our paper up to the end of 2021. I'll return to this this figure in a few slides when I discuss the results and essentially how well this worked. It was able to essentially perfectly classify, hierarchical clustering applied to this quantity, DXY, was able to, between the 50 US states and DC, was able to perfectly classify in one fell swoop all the different US states into essentially at the height of the first wave, over the first wave, at the height of the second wave, and over the second wave, as well as reveal additional data, as well as reveal additional kind of elegant insights, which I'll talk about in a few minutes when I get to the results section. But the distance, as everything in this talk has serious limitations. So essentially, this distance between finite sets, and many distances between finite sets, encounter difficulties when you might have one set that looks like this. Here are the elements of the set, and then you might have another set with many more elements. Okay, and if these were, say, peaks and troughs or just peaks, obviously the first state would, you'd want to declare its wave behavior very different from the second state. However, there are always these kind of issues with distances between sets where they are rather small when one set, they can be rather small when one set is a subset of another set. It essentially, whenever you form the Hausdorff distance or the modified distance, or the modified squared Hausdorff distance, you have many quantities going to zero that add up to the overall distance when you have many elements being in the other one. And yet, if there's a great difference in cardinality of the two sets, you really do want to say that the wave behavior is quite different. So this distance is imperfect. And it gets more imperfect as the data gets larger, and you just have more and more waves being detected, which is sort of inevitable because more and more waves do occur, and it would be wrong to refine too much, when there are really, there are very significant waves that we've all suffered through. And so we came up with some ways to force them apart in subsequent papers, such as penalty terms for the difference in cardinality. Honestly, this felt to me a little bit like cheating, in a kind of complicated sense that I might not be able to describe, but I'm certainly interested in kind of completely alternative ways to really distinguish wave behaviors apart. Whether that's based on distances or something else. Clear all drawings and decks. Okay. Now, again, I'd just like to talk briefly about the results of 2 papers that were dedicated to COVID-19 wave behavior. So again, I return to this picture. And again, to state this picture, this picture, which is the result of hierarchical clustering on the distance defined above between determined sets of peaks and troughs, was able to classify these states as having identical wave behavior, namely just simply one wave, beginning at t equals 0 and ending at the final day of data. These states, New York and New Jersey, being rather exceptional at that time, having experienced a first wave with no second wave, conquering the second wave. These states, Vermont and Maine, very small states, they had relatively unusual behavior. They were detected to have 2 completed waves. Utah and Arizona, also unusual. They were the only states which were really had a first wave and then were in the period of decline, with no trough detected yet. And all of these states, from Washington down to Iowa, were detected to be in their second wave. But the insights didn't stop there. The split in this large purple cluster here also revealed something small and interesting to us, that essentially Washington down to Florida had a relatively late second wave, or relatively late beginning of the first wave and beginning of the second, whereas these states from South Dakota down to Iowa, including these northeastern states like DC, Massachusetts, and Connecticut, they had a relatively early first wave, and then the second wave began much quicker than in these states up here. So I think that this figure was, really everything that I wanted to be. Some elegant maths that was able to do the classification task that I outlined right at the start, perfectly essentially, and reveal some initial insights. So I was very happy with this. Okay, and so that's the kind of the main results that I'd like to present to you. And I'm running out of time, and I think I don't really have the kind of the space to talk about the next paper's results in detail. But in another paper, we analyzed the second wave in European countries, with data that went, I think, until the end of 2020 or the end of November 2020. And the application there was to use this wave partition analysis to examine and appropriate offsets between the cases and deaths time series to examine the change in case to death mortality or fatality between the first and the second wave. The story at the time in all the press was that, and indeed in data that my friends were sending me from their countries, was that in the second wave, cases had shot up, but deaths were much slower. But good news. In other words, that the case to death mortality rate had decreased substantially between the first and the second wave. And so I thought, let's analyze this on a country by country basis. And sure enough, we found that certain countries that the media had focused on, France, the Netherlands, the UK, had experienced a significant decrease in mortality between the first and the second wave, but that the media had really ignored the full heterogeneity within Europe and the full story, which is that some countries were even in a very late first wave. They hadn't even had a first wave in the second wave. They were still in their first wave as of November, with giant cases that dwarfed early on, and that some countries, their they experienced no reduction of mortality between the first and the subsequent wave, which really had not been adequately discussed at all. That there was, substantial heterogeneity, especially between wealthy Western European countries and less wealthy Eastern European countries. And another paper that I just want to mention, because it's actually what I think I've originally invited my colleague Nick to present, was a paper about wave analysis in the US, Brazil, and India. These are 3 federations, each with not exactly the same, but similar responses to the pandemic, with the federal government kind of taking a hands-off approach at some points. They're not exactly the same, of course, and substantial heterogeneity between states in terms of how the individual state governments or territory governments, provincial governments reacted. And so, that was another paper. Again, probably don't have time to discuss anything about that, but I just wanted to acknowledge that, as that was, what we invited to discuss initially. So that was another application of this wave behavior, really analyzing the 3 different federations as whole units, and how their wave behavior, as well as other aspects of COVID cases, differed, in intra-federation and inter-federations. Okay, and I guess I'll end with some ramblings. So I've always found COVID time series to just be bizarre, right? I've found, even before the new variants observed, the behavior of COVID-19 cases, I think was very complex to me. I think it was, we do have SIR models that incorporate a reinfection component, and they do predict, oscillating behavior. But what we've seen even before the new variants was really nothing like that, right? And I think that there was a great deal of complexity. But despite that complexity, as I look, everything really seems to come down to 2 questions: where or when, because it's in time. When are the waves, and are they exponential or linear? I think that's a rather reductive question, but almost all the time I look at the data and it looks exponential, and then it suddenly switches and it looks linear, with a slight period of concavity in which it changes from upwards linear to downwards linear. So I guess I should ask, where are the waves? Where are the exponential periods? Where are the linear periods? Where are the switches? And that, I guess, motivates my desire to always, to look at these waves. And I think that just COVID, the whole pandemic has been so complicated, especially regarding these waves, that obviously I've called for more mathematical approaches to do a better job than the methods that we've come up with. But in addition to better mathematical methods, I think that these waves, they absolutely have to combine. They absolutely have to combine as a perspective, perspectives of they absolutely have to combine. Psychological, political, and epidemiological perspectives in terms of what is driving these sudden changes. And I'm talking to an AI crowd, so could we use massive neural networks to interpret all the data we have, including text analysis, including all sorts of things? I think that might overfit. I think that might overfit substantially. And so I don't know. And so I think that, personally, I would like to see. I don't know how to understand these waves, and I would like to see a combination of simplicity, but better more cross-disciplinary discussions and incorporations of other perspectives, but not an excessive amount of data from other perspectives that could lead to overfitting. But I think, but simpler approaches. So in the same way that I think the mathematics in this paper is relatively, it's not the most complicated. I think we take targeted and simple approaches. I would also like to incorporate, targeted but simple truths from other disciplines, and I don't know how that would work. So, I leave to everyone, plenty of ways that our mathematics can be improved, and more mystical ways that other perspectives could be incorporated and everything could be improved. Because, as I said again, the pandemic's extremely complicated, but I think that the wave behavior is almost at the heart of it. Yeah. Anyway, so that's it for me. Any questions? Here's some references. Yeah.
Thanks, Max. Great talk and interesting topic. Are there any questions from the audience?
Yeah. Hi, Max. Yeah, I second. Great talk and nice to finally meet you. We didn't hear neither the tradies nor the crying, nor the tradies crying. That would have been interesting. So this notion of waves, or one can think of them as episodes, they're kind of, it's interesting, but I want to ask you we've also been interested in it here, kind of looking at episodes of, they start, they end, etc. But I want to ask something about the following. So if you in mathematics, sometimes or in mathematical modeling, we sometimes believe there's an underlying state, and the state is kind of the description of everything, right? We're reading this univariate time series, and it's one reading that's kind of a projection of the state onto some measurement. And if you go even to a simple example of, say, a second order ODE, where there is, the state is two-dimensional, and you look at the output response of this, you can get oscillations, and that would imply waves, but the relation between the waves and what's happening actually in the state space is not so clear. There's not a kind of a clear relationship, right? I mean, you can analyze a system with a given model, a linear system, etc. Say it will have oscillations when you do the output of it or not. So I want to kind of ask philosophically, from how would you relate waves to the original state, if at all?
Oh, see, I guess that's what I was getting in my ramblings. So I have always found these waves to be fascinating, as of other researchers. So many articles have written, what's going on, why do we have a precipitous decline? So, and I think that also was with my first kind of question, like my first observation. That's maybe we should describe rather than predict, because I guess the answer is I've never known at all what's the underlying state, but beneath the waves. They are so confusing to me. So let's see. So yeah, I guess the answer is I don't know. I try and yeah, this is the other perspective that I was calling about, that I was calling for, because I think that I think we need clearer, sometimes simpler maths to kind of really describe, where the waves are, but what is driving them is a complete mystery to me, and always has been. I think the new variants pose some answer, but even before then, even before then, I've in Australia and around the world, I find them completely bizarre, yeah, it was. I I guess no, I'm continuing my rambling without. Yeah, so I guess I guess I don't know at all. You know, from what happened in Fairfield, you know, to what happened in the United States in December 2020. I'm consistently caught off guard by trying to by these waves, and so I'm consistently perplexed by the states. And yeah, I think this is. I have no answers to this, but I think there's. I think some. I think for future pandemics, there needs to be some kind of transformational research change where you know very different disciplinary researchers come together and invest and discuss and figure it out. Because I have no answer. It's my ultimate. Yeah.
Okay.
Yeah.
Thanks.
Any other questions?
I have a question, but it's on maths question. Sorry, Max. Thank you. It was a really good presentation. I'm not a maths person, so I didn't understand all of it. I'm an epidemiologist. And maybe this isn't the purpose, but I guess just based on your motivating questions, there's like a lot of appetite for this type of work in public health, but we don't always understand everything and people find it a bit scary. So if you can understand and describe the waves, how do you see, do you see that being useful for people working? Like, how would you see this applied or being useful for people working in public health for future pandemics?
How do I see this being applied? So first, I do think wave behavior is very important. I think wave behavior is very important. I think by its nature, it greatly simplifies these complex time series, which, you know, are, I guess let me start again. So you know, public health is very interested in modeling and predicting the future. And I think that you know, there are all sorts of very simplifying quantities and assumptions like SIR models and calculating R naughts, and they don't think work that well. And so I think that looking at wave behavior may simplify and hence bring more light to the nature of yes, it's okay to share my slides, the nature of what's happening. And that I think it's very important to simplify mathematics so that, you know, so that other people can set that, so that everyone else can use it. That's number one. Number two, I think that I would certainly like and the rudimentary and kind of the rudimentary analysis that I've done on waves to be improved, and then I think it could be very useful for public health research. So, for instance, I aimed. I'm a pure mathematician at heart. So, approaching COVID-19 in the United States, I began with, you know, kind of a pure mathematical, you know, let's find something that's mathematical, elegant, and does a classification task well. But then I did notice something, a small insight that I thought, you know, that wasn't something that I knew in advance. You know, this distinction between the second wave states in terms of whether they had an early wave or a late wave, basically. And so, subject to, you know, improvements on, you know, wave behavior analysis and detection, yeah, I would absolutely hope that more insights like that would be gleaned from, you know, looking at collections of countries. This is, you know, one very small insight, but, you know, I'd like way more insights, and then I hope that, you know, something like that can, you know, something can be seen, right? And that can something that can be seen. And so, for instance, you know, you're not a mathematician, but this thing about early first waves versus later first waves ending, that can definitely be communicated to you know, non-mathematicians, and then and yeah, so I'd like better methods to find better insights which remain easy to communicate. Yeah, so I guess sorry, I think what was the original yeah, so I think that I guess so. So to summarize, the uses would be simplifying the complex mathematics of COVID-19 time series into discrete waves, which are better to understand, and subject to better methods than mine, finding insights such as this very small insight that can be easily conveyed, and then this kind of big transformational mystery step that Yoni alluded to, then trying to work closely with people of different disciplines to understand what's really going on behind these waves. That I think that I don't have a clear kind of idea of how that would work, but that could be of immense importance in future pandemics, right? Understanding these kind of these shocking waves as much as possible. So I hope that was I hope that answered the question.
Yeah, I think one thing you could do to start those conversations that I've done previously is like writing this for a public health audience. Like it doesn't have to be a full paper, but you could write sort of like not like a review paper, but almost like an opinion piece and describe your work to a public health audience and how you see it working. They're very popular in the past, and I just think that's a good way to start those conversations. If you ever wanted to start those conversations, I think that's a good way to go about it.
I was considering doing something. I mean, I was actually considering doing something like that. I was going to write a commentary to the. I was going to write a commentary in a. Similar folks have written in the Lancet. Mathematicians writing small commentaries, and this has nothing to do with my talk. But I think that the measure of excess mortality is imperfectly used by public health people, because it can be. We studied it quite closely in so essentially as I mentioned, there's this also my talk. These are other results. We studied the second wave mortality in Europe, and we did it first for confirmed case and death data, and then for estimated true cases and death data. And for the estimated true death data, we used the excess mortality, and we discovered something vaguely interesting, that the excess mortality is often negative, and so whenever you use it, you have to be very careful about whether you're zeroing out negative numbers, or you're integrating you're adding negatives, and so you might be anyway. So that was just a comment of something that I've thought of that would be but I think that's a good idea.
Okay. Any other questions? Thanks. Can I ask one question? So if you go to Georgia, the picture that you have shown for Georgia, okay. So in this picture, did you say, like, according to your method, the first peak is not considered as a wave? Like,
so the first detected peak is right at the end of the time series. So the whole thing is one wave. So Georgia,
right.
so as of the end of July, I think that's at the end of July, Georgia was still in its first wave, right? It had no discernible period of decrease at all, right? And so, actually, I guess that's, yeah. So I think that could be something for public health folks like Emily to go on. Sorry.
When you say there is no discernible peak, that did you mean like this little peak over there, and then you didn't see a decrease? Is that why you said it?
So you can annotate if you like, but so this very slight local maximum in the smoothed cases. I mean, obviously there is a 1 day peak there, but it's kind of cancelled out by the next day of data, essentially. So this isn't. I mean, this isn't real, I think, in a sense. And so this very slight peak was determined from here to here, was determined not to constitute a non-trivial decrease. So this was not declared. this was not declared, you know, a wave. This was just, and I think this is quite appropriate, because I don't think, looking at these numbers, that there is really any significant decrease in cases. I think that, you know, in terms of public health, the moderate measures that Georgia imposed, I think Georgia was famous for its governor overruled mask mandates, and so it really had only very moderate measures that they essentially created no decrease of cases at all. So to to remove restrictions around here was quite foolish, because, you know, there had been no decrease at all. So with the removing restrictions, it would just have exploded, off which it did something too, which was relatively surprising to us, because California was featured in the media as, you know, an excessively strict state, but in fact, California removed restrictions after no period of decrease, no amelioration of the state of the pandemic. Yeah.
And your data, like the data that you've shown here, is it like smoothed over?
Yeah. So we've got raw cases and the smooth. The blue is the smooth.
Oh, so like the actual data is not smoothed.
Oh yeah. So the gray is of the raw new daily case counts.
Yeah, but okay. So the new data cases are not smooth, but your feeding is smooth. Like
that's right. Yeah. So these are just the raw daily data, and the smooth function incorporates averaging as well as smoothing.
Okay.
Like seven day averaging and then smoothing.
And like the methodology is in which paper? Like I know you have quite a lot of papers in.
Oh, we essentially always, for the smoothing, combine a 7-day averaging and then a Savitsky-Golay filter.
Okay. Yeah, I'm really interested in this peak detection and like start and stop of the waves. So that's why I said, like, is it okay for you to share the slides?
Oh yeah, of course. And we have more states like this in the paper. So I think yes. So California and Texas are both quite interesting in that they experience no discernible period of decline and then go up, and they're declared to be in their first wave at the end of the data set, which was, you know, July 2020. This is a slightly old paper. And, you know, we present many examples of second wave states as well. But I can show you more pictures now if you like, or okay. They're not in this document. One sec. Where are they? I need to exit that. Okay, I will share again. Okay, so there are there's some more examples. Sorry. Where is California? For California really has no decrease at all. There's no refinement necessary. Yeah, so there are various states here that have been featured. And yeah, is there anything you'd like to see in particular?
Yeah, it's kind of interesting. Like when you showed me like the Florida wave, like that red, between the red and the green vertical lines, the first. So according to your method, is that a wave? Like, is that entire time series a full one wave, or it's just two waves?
Yes, so Florida's two waves, and I illustrate this as like a borderline case where it takes one thing for this is a borderline case between Georgia and Florida. That was my intent of including those two in the talk. That was a tough call, essentially, and it just depends on the parameters. Yeah.
Oh, okay. Yeah.
Yeah. But no, I mean, if you're skeptical, you're absolutely right to be skeptical. This is an interesting and difficult mathematical problem, and depends on parameters. And we kind of investigated and set our parameters. We investigated. We kind of prioritized. I guess relatively simple mathematical elegance, and then just kind of chose parameters at the end of the day. But of course, you could do all sorts of parameter tuning and more complicated things. Yeah.
All right.
Yeah, but you're right. This is interesting and challenging. So if you're skeptical, you're right to be skeptical, because we did our best with a challenging little problem. Yeah.
Thanks.
Oh, you're welcome. Yeah.
Yeah. Any other questions from the audience? We are almost time. Okay, if not, shall we all thank Max for his great talk and spending time with us? Thanks a lot. It was great meeting you, and then interesting topic, at least for me. Okay, thank you.
Oh, thank you so much. Thank you so much.
Bye.
It's been so hard to visit it anywhere in Australia for so long, but I'll visit at some point.
Okay.
Yeah, I just visited the first state outside New South Wales and Victoria for a very long time. Yeah, I went to Tassie. Anyway, so it's been so hard to those two states have just been locked, in one of them for so long. Yeah. Anyway, thank you so much for inviting me.
Thank you.